binding energy curve, nuclear fusion, and nuclear fission. A nucleus is a bound system of nucleons. This means that the work done by the attractive strong force is transformed into a type of potential energy. In the past, I had a nucleus that has protons and neutrons. If I focus on just one of these, either the proton or the neutron, I can replace this binding as a potential well, where this is a trapped nucleon. And this is the binding energy is the work required to remove a single nucleon. As the number of nucleons increases, the strong nuclear force also increases, simply because there are more nuclear bonds. A useful measure of comparing one nucleus to another is the quantity binding energy per atomic mass, which I'll write as Be divided by A, where A is the atomic mass of an atom. What does binding energy per nucleon mean? Remember, binding energy per nucleon is Be divided by A. This is the amount of energy you would need to supply in order to remove a single nucleon from the nucleus. Nuclei with larger values of Be over A are more tightly held together than nuclei with smaller values. Analogy: pulling a water bucket out of a water well. Imagine that I have a well here that's not as deep as this guy here. So as the bucket goes down and you got to pull this water, the fact that you're not going as big of a height, it takes less work. So in the language of binding energy, this would have a lower binding energy. However, if this well is deeper, that's clearly going to be more work. Therefore, in the language of binding energy, this would have a higher binding energy. Applying this to nucleons, if I have a lower potential well, that trapped nucleon has a lower binding energy per nuclei. Therefore, it's less tightly bound. If I have a deeper potential well, then I have a higher binding energy per nucleon. Therefore, the nucleons are more tightly bound in the nucleus. The binding energy curve for stable nuclei is shown below two different ways. On the left, you see that the curve curves upwards, whereas on the right, they curve downwards. It turns out that binding energy is negative, and this is actually the more correct one. This one's, although it's correct, it doesn't have the right direction. The curve on the left here shows that the atom with the highest binding energy per nucleon is just to the right of iron 56. So it's just to the right, right in here. The highest is 62 nickel, and it's followed by iron 58 and 56. The second curve shows that around 60 is where you're seeing it, not 56. So it is the curve on the right that we will focus our attention on to explaining what we're going to be looking at right now. Not the left one, but the right one. So interpreting the curve on the right, note that the ground level, here is 0, is indicated by 1H, hydrogen 1. Hydrogen 1 has only one proton in its nucleus, and therefore it has 0 binding energy. There's nothing there there's not more than 2 nucleons to bind. So that's what we call the ground level. The next thing that I want you to note, look at these numbers. These numbers are negative. They start at 0 and they go down to about -8 to -9. The negative values imply the potential well goes below 0 or into the ground. So if it goes into the ground, I can draw potential wells for different nuclei. Let's do that. So I've drawn 3 wells. There's lithium-6 right here. And you can see that the depth of the well goes down to here. Here's iron 56, goes all the way down to here. And then there's uranium-238, which goes all the way down here. The depth of the well gives us information. This well tells us that a nucleon trapped in lithium-6 has less binding energy than the nucleon trapped in 238 uranium. Why? because this is a deeper well than the lithium one. But the stronger potential well is that for iron 56 because it's deeper. Therefore, because iron 56 has a very deep well, it has one of the highest binding energies of all nuclei. Let's interpret the flow of the binding energy curve. For small mass nuclei, that is values below 60, by adding more nucleons to its nucleus, it increases the binding energy because as I add more, I go deeper into the well. Once again, as nuclei move down this potential well, nuclei increasing binding energy per nucleon. Maximum binding energy per nucleon occurs around the atomic mass 60. Nuclei with atomic masses greater than 60 become less stable as their masses increase because adding more nucleons decreases the binding energy per nucleon. So if this is 60, as I start to go up this ramp, what you're seeing here is that the potential wells are getting smaller. And if they're getting smaller, that means that the nuclei have smaller binding energies and therefore less stable. So as the nuclei go up the ramp, the nuclei decrease binding energy per nucleon and therefore are less stable. Up to this point, we have talked about the most common types of radioactive decays, alpha, beta, and gamma. I now want to introduce two new nuclear processes, fusion and fission, which are easier explained using the binding energy curve. Nuclear fusion. If two light nuclei can be joined together, it's a forced union, to make a single larger nucleus, the final nucleus will have a higher binding energy per nucleon and therefore more tightly bound. During this process, energy will be released. This process is called nuclear fusion. What does nuclear fusion look like on the binding energy curve? So, if I have light nuclei here and somehow they get fused together, that means that one of these nuclei will be the heavier final nucleus. What happens then is that this is the direction of higher binding energy. To the left of the green line is only fusion. When light nuclei fuse together, their final larger nuclei has a deeper potential well and becomes more stable. It slides down this sort of ramp in the nuclear potential. To really get an understanding of nuclear fusion, let's look at an example. The sun is primarily made of hydrogen, but the electrons are not attached to the protons. Nuclear fusion of hydrogen to helium is a basic reaction that powers the sun. This is a two-step process for the fusion to occur. So in the sun has a lot of isolated protons, and these isolated protons are going to interact with each other such that you get the first step, which is an inverse beta decay. So in the sun, there is an inverse beta decay that converts a proton into a neutron, forming deuterium, which is hydrogen 2, an isotope of hydrogen. So that means here is that I have a proton and a proton, and if they interact enough, I'm going to get beta inverse. And what happens here is that these two protons then spontaneously, you're going to have one convert to a neutron. So this proton converts into a neutron, and so then it releases a beta particle and some energy here. Now we get to the second step, nuclear fusion. Inside the sun, there are very high pressures and temperatures. Because of this, a proton and a deuterium atom are forced to fuse together, and they form an isotope of helium, helium-3. So that means then that the sun, here in purple, is pushing these two together. And when they fuse, they now become helium-3 with the emission of a gamma ray. So the nuclear process here has a proton plus hydrogen-2 deuterium. They fuse nuclearly and they produce helium-3 plus gamma. This helium here is literally the birth of a helium atom. This atom cannot be made on Earth, but it can be made inside of stars. This gamma ray is a light energy released from the nuclear fusion reaction, and this accounts for all of the light that's emitted by the sun. The thing here is that this happens at the center of the sun, and it takes this gamma ray 100,000 years to leave the sun and reach the Earth. The binding energy curve, what does this mean? Note that I have hydrogen, I have deuterium right here, and I have helium-3 right there. A proton has no potential well depth since it's only one nucleon, so we know that the binding energy of a proton is equal to 0. Because deuterium is a bound system between a proton and a neutron, there's a nuclear bound binding energy and it has some depth. So in this case here, so when I look at the deuterium, you could see that the value is -1, so its binding energy is -1. If you look at helium-3, it has more nucleons, and therefore its nuclear binding energy is stronger. Stronger means a deeper well. So when I look at helium-3, you could see here that its binding energy is about -2.5. Let's now look at this nuclear fusion reaction from an energy bar perspective. From the binding energy curve, we know that the binding energy of hydrogen, a single proton, is 0. There's only one nucleon. When I go to deuterium, hydrogen-2, there's a neutron and a proton that are bound together, and we saw from the graph that that was -1. And then we have the binding energy of helium-3, and off the graph it read -2.5. So if I look at the bar diagram, for the binding energy of deuterium, it goes down -1. For the binding energy of helium-3, it goes down -2.5. So there's an energy difference between these two systems versus that guy. I'll label this energy difference as delta E. Once again, the energy difference between a hydrogen plus hydrogen-2 versus helium-3 is this delta E. Written out, delta E, the energy difference between two unbound nuclei versus a single bound nuclei. This difference in energy is then the energy of the gamma ray released by the nuclear fusion process. So it's the energy difference between these two minus the energy difference of this guy, and that difference then is the energy of the gamma here. Let's go through the numbers again. The binding energy of hydrogen plus the binding energy of hydrogen-2 is 0 minus 1, which is equal to -1, versus the binding energy of helium-3, which is -2.5. -1 implies that there's more energy than -2.5, which has less energy. The way I'll show you this is through the number line. Think about this through the number line. If you look at -1 versus -2.5 on this number line, it turns out binding energy of helium-3 is a more negative number, so that makes it smaller. On the other hand, the combination of hydrogen plus hydrogen-2 binding energy is -1, and that's less of a negative number, so that makes it bigger. So there's more binding energy in hydrogen and hydrogen-2 being separated than the combined system that now forms helium-3. If I readjust the energy bar diagram to make it look like the ones that we studied when we studied energy, the binding energy of hydrogen to hydrogen-2 is much larger than the binding energy that created helium-3. It's this leftover energy that goes into this gamma. Final note, nuclear fusion is not a spontaneous process like alpha, beta, and gamma, but it is a forced process due to the super high internal pressures and temperatures inside the sun. However, there is another spontaneous radioactive process known as nuclear fission, which we now discuss. Nuclear fusion. Earlier, we talked about heavier nuclei, more massive than lead, were unstable, and most likely spontaneously decayed via alpha decay. And it's this yellow part of this band of stability that led to alpha decay. There is a second type of nuclear reaction that is also spontaneous, but more specialized, called nuclear fusion. We can see this on the band of stability in the lime green region. That is, it's this very small region of particles right in here. This is a nuclear reaction in which a heavy nuclei spontaneously splits when impacted by a slow neutron, although this is not necessary. And there is a release of additional neutrons and energy. Picture-wise, it looks like this. So there's a neutron. That neutron is sometimes called a thermal neutron, and then you have a target nuclei. What happens here is that this neutron is literally captured by this nucleus. This is called neutron capture. When it captures this green neutron, which is that guy right there, this nuclei is now highly unstable because of this capturing of the neutron, and then it spontaneously fissions. That means that there are two typically big fragments. They're called fusion products. And there's a release of additional neutrons and energy. This process right here is called nuclear fission. So notice that one starts by shooting a neutron at a target nuclei. Why? If one shoots a positive proton at the nucleus, the positive proton will be strongly deflected by the repulsive electric force of the positive nuclei. If you want to get into the nucleus, you need to shoot a neutral neutron because they don't feel the repulsive electric force of the nuclei. Picture-wise, a proton coming towards the nucleus feels this repulsive electric force and it gets deflected away. But if I have a slow neutron, known as a thermal neutron, it doesn't get deflected by the repulsive electric force, and the nuclei then captures the neutron. Example, nuclear fission reaction of uranium-236. Here's a nuclear process that has neutron capture that leads to the fission of 236. I first start off by having a thermal neutron that is then captured by 235. As soon as the 235 absorbs a neutron, I now have uranium-236. This is highly unstable, and 236 immediately fragments by fission. Then there are two fission products, barium-144 and krypton-89. They're less massive, but they're more tightly bound than the original 235. One of the key signatures of nuclear fission here is that there's a release of extra neutrons. There's the one coming in, and then you get another two that come out. Picture-wise, the neutron comes in, gets captured. I get now 236 because of that extra green neutron, which is highly unstable. And then this guy spontaneously fragments into barium-144, krypton-89. I get my three neutrons plus this extra energy that's released. Now the important signature of fission here is that this neutron is the same as these other neutrons that they're released. Let's now look at this fusion reaction on the binding energy curve. We know that around iron, those are the most tightly bound nuclei. So we start off with 235 here, and then when it goes through the process of neutron capture and then fission, the products are barium 144 and krypton 89, note that you're moving down this binding energy curve, saying that you're moving in the direction of more tightly bound nuclei. Once again, as nuclei move towards the bottom of the curve, that is the direction of more tightly bound nuclei. Just like alpha, beta, and gamma radioactive decays, fission reactions move less stable particles towards more stable particles, and in this case, more tightly bound nuclei. However, barium-144 and krypton-89 are still radioactive, so their decay products will continue to slide down towards the bottom of the curve. Written in words, these fission products are unstable. That is, barium-144 and krypton-89 are radioactive. They immediately decay via beta decays. So these two decay via beta inverse and beta regular beta towards iron-56. In general, these are the waste products of nuclear fission. This has important consequences for the use of nuclear fission as an energy source. More on this when we reach the topic of magnetism. The physics of a nuclear bomb. There were 2 nuclear bombs dropped on Japan at the end of World War II. Hiroshima was a 235 uranium fission bomb, while Nagasaki had a 239 plutonium fission bomb. We need to make some new definitions. 1. When uranium is mined, it does not have enough concentration of uranium-235. Natural uranium contains 0.72% of uranium-235. This graph over here is from Wikipedia, and you could see that uranium-235 is what you need for the fission bomb, is this little tiny sliver. In order to make a bomb, you need to go through the enrichment process too. The enrichment process is to increase the percentage of uranium-235. Why is uranium-235 important? It is the only nuclei that exists in nature that is fissile with thermal neutrons. That means it's capable of sustaining a nuclear chain reaction, and these thermal neutrons are those slow neutrons that we were talking about earlier. 3. Highly enriched uranium, which is known as weapons-grade uranium, contains 20 to 85%. The bomb dropped over Hiroshima was called Little Boy, and it contained 64 kilograms, or 141 pounds, of highly enriched uranium of 235 at an average percentage of 80%. When the bomb went off, less than 1 kilogram went nuclear fission, which was transformed into several forms of energy, mostly electrical kinetic energy, which we already talked about, but also heat and radiation. So this enrichment that they're talking about is this case right here. 4. If there is enough fissile material, that is enough of highly enriched 235 uranium atoms, then a self-sustaining fusion chain reaction can occur. Every fission reaction releases a small amount of energy. Let's try to explain this chain reaction in detail. This chain reaction is that every fission caused by neutron capture by 235 causes 236 to undergo fission, which in turn produces 3 thermal neutrons. So that first red neutron, after it goes through some fission, then produces these 3 green neutrons. But these 3 neutrons that are green are the same as the red. Each of these thermal neutrons cause new fissions, which then each in turn produce 3 more additional ones. So that means if I look at this green one, when it then hits a 235 uranium nuclei, it produces 3 more blue neutrons. And then that one produces 3, and that one produces 3. So what you're seeing here is that there's a chain that starts to occur. The red neutron produces 3 green ones. The 3 green ones produce 9 new blue ones. Then these blue ones go on to create 27 new orange neutrons. And then these orange neutrons then produce 81 purple neutrons. And it's this chain reaction that's super important to a nuclear bomb. So then if I look at this chain reaction, here I go. The first neutron causes neutron capture and fission, and then it's this release of energy right here that's very important. And that release, you get 3 neutrons. These 3 neutrons in highly enriched uranium are going to find 235. And then from that 235, you see that little red starish type thing, that's a release of more energy. And then those 3 neutrons go on to do what? Hit 2 other 235s, and you could see all these little red stars is the release of energy. It's this release of energy that is multiplied roughly to Avogadro's number, that is the release of an enormous amount of energy. And that's how a nuclear bomb's underpinnings work.